We've seen how to graphically use a acceleration graph to find the velocity, the change in velocity due to that graph. Here we're going to see how to do the same thing, but analytically. Basically, we're going to be given the acceleration as a function of time, and we'll be able to use that to find the velocity at any time later on and the position at any time later on. We said that the acceleration is the time derivative of the velocity, and so the velocity will be the antiderivative of the acceleration as a function of time. And so we'll see here if our acceleration is given as a polynomial expression. Then our velocity can be found by taking the antiderivative of each piece. Here, if we take the antiderivative of t squared, we will get a t cubed term. And when we pull out the factor of 3, we will end up with a 4 out front instead of the 12. Similarly, when we integrate t, we'll get t squared. But when we pull the 2 out of the 6, we will be left with a factor of 3. When we integrate 2, we get 2t. However, because this is an indefinite integral, we also get a factor, a plus c, an arbitrary constant. In order to find out what that value is, we have to use our initial conditions. We're told that at time t equal 1 second, our velocity is -2 meters per second. So we can plug that in. If we know the velocity, we know the time, then the only unknown in the equation is the arbitrary constant, and thus we can find that value from these initial conditions. So we're saying that -2 is the velocity when time is equal to 1. So here we have a factor of 4. 4 times 1 cubed is 4. 3 times 1 cubed is 3. -2 times 1 is a -2. When we add all these up, 4 and 3 is 7, less 2 is 5. To get c by itself, we find that c is equal to -7 in this case. So what we do is we can take away the c in our velocity equation, and we can put our -7 in its place. Now that we have the velocity, we can find the position by the same means. Since the velocity is the derivative of the position should be the integral of the velocity. So to integrate again, our t cubed becomes a factor of t to the 4. Our t squared gives us a factor of t cubed. Our 2t becomes a t squared. And when you integrate -7, we get -7t plus c. We get another arbitrary constant. It's the same way as before. Looking at time equal 1 second, we know the position. And so if we know the position at a fixed point in time, we can find out what that arbitrary constant has to be due to our initial conditions. So x of 1 is 3 meters, but it also comes from the equation we just found. Here we see 1 cubed minus 1 squared cancel each other out. We see here 1 minus 7 will be -6. And in order to solve here, c must equal 9. If we found a value for c, we can replace the c from our position graph, our position function, and put our arbitrary constant back in. So thus we've used the acceleration as a function of time. We've used initial conditions to find the velocity as a function of time and the position as a function of time.